Hello, dear students, you are welcome in this class. And today we have a practical determination of organic carbon or organic matter in soil. So we do not measure organic matter directly in the soil. Practically, we measure carbon or organic carbon, then convert it to organic matter. So if we know organic carbon, we can know the organic matter. So it is mostly estimation of organic carbon, and then we get values of organic matter. Today we are going to learn determination of organic carbon in soil by Walkley and Black method, and the reactions of oxidation of soil organic carbon and some reactions during titration. And then we will have some calculations and numericals. So as you know, soil organic matter is most important soil property, which is basically a chemical property, but it influences both physical and biological property also. It holds water and plant nutrients, supports soil organisms, and it is necessary for a healthy soil. Total soil organic matter is estimated by ignition or by kind of volatilizing the carbon. And then this is measured. Suppose you have a mechanism to burn the carbon or ignite the carbon under controlled conditions at high temperature, then CO2 will be evolved. And one can measure the CO2, and that can be correlated to the organic matter content. So this is done by total carbon analyzer. We have got one equipment, the name is TOC analyzer, total carbon analyzer. And however, that is expensive and not available everywhere. So rapid chromic acid oxidation of readily oxidizable soil organic matter is most popular and practical way. So rapid chromic acid oxidation is Walkley and Black method, through which we estimate the oxidizable soil organic matter that can be oxidized by chromic acid. However, it cannot oxidize all organic matter present. It cannot oxidize the inorganic carbon. It cannot oxidize the stable carbon, which is in elemental form, carbon form. So it recovers only 77% of the carbon present, organic carbon present. As you know that why do we estimate carbon? Why we are estimating organic matter? What is the purpose of estimating soil organic matter in the soil? Because it influences soil fertility directly. So in general, higher the soil organic matter, better is the soil fertility. And we also can fix the limits of soil organic carbon. You have already seen the rating chart, and we can fix the limit. If we know that this particular soil, this particular field has so much of organic carbon, then according to that, we can put it in the limit, whether it is deficient or sufficient. If it is sufficient, then there will not be need to add organic matter. But if it is deficient, the organic matter should be added to the soil. Thus, practical management. For practical management of organic matter, we need to estimate the CN ratio. If we know the carbon content, organic carbon content, then we can determine the CN ratio. Because CN ratio is very, very important for supply of nitrogen. So we can indirectly estimate that what quantity of nitrogen is available. Carbon sequestration. It is important to understand carbon sequestration. Suppose this year, carbon content in soil was 2%. Next year, suppose it becomes 2.5%, or say after 5 years, it becomes 2.5%. Then how much carbon increase is there in the soil? So such kind of studies or estimates can be made if we know the soil organic matter levels of our soil. Now, one question is usually asked from the student that what is total carbon? So total carbon is practically organic carbon plus inorganic carbon. So organic carbon components are already known to you. It may include your slightly processed organic residues of plant and animal origin. So organic matter is always from the living things or living organism give organic matter. So it may include your slightly processed organic residues of plant and animal origin. Humus is also part of organic matter or carbon, charcoal, fossil organic matter, and microbes. Inorganic carbon, you must remember, it is mostly or rather only carbonates and bicarbonates. So carbonates may be associated with some positively charged atoms like your ions or atoms or materials, chemicals, you can say, like your sodium carbonate, calcium carbonate. Mainly it is calcium carbonate and calcium bicarbonate, magnesium carbonate, etc. So these are inorganic sources of carbon. So this is Walkley and Black method 1934, and it is still most common in developing countries, laboratories. So certain chemicals are required for estimation of organic carbon in this method. And we need to know the molecular or equivalent weight of these chemicals to prepare their solutions. So as discussed in one of the lectures, you know, for normal solution, you need equivalent weight. For molar solution, you need molecular weight. So molecular weight of potassium dichromate is 294.19 gram. So you can work out the equivalent weight of potassium dichromate. So equivalent weight is 49.04. Here the valency of chromium is +6. So 294.19 divided by 6, 49.04 is the equivalent weight of potassium dichromate. So it is the main reagent or main chemical used in estimation of carbon in Walkley and Black method. Then molecular weight of ferrous sulfate. Ferrous sulfate or ferrous ammonium sulfate is used for titration purpose. So molecular weight of ferrous sulfate is 278.01 grams and equivalent weight is 139. Molecular weight of ferrous ammonium sulfate. Ferrous ammonium sulfate 6H2O. So it is hexahydrate. It is hexahydrate 6H2O. Ferrous sulfate FeSO4 7H2O. This is heptahydrate. Ferrous ammonium sulfate is actually ferrous sulfate and ammonium sulfate. So all are one compound, FeSO4 ammonium sulfate 6H2O. The molecular weight is 392.13 and equivalent weight is 392.13. So in titration, you can use either of these two. You can use ferrous sulfate or ferrous ammonium sulfate. One of these salt is used for titration purpose. The results are same. It is your choice to use. But in our laboratory, we normally use ferrous sulfate. Now, how to prepare these reagents or solutions? So one normal potassium dichromate. This is to be prepared. This will be used in the analysis of organic carbon. So one normal potassium dichromate. So this metal agreements. So one normal potassium dichromate, it is prepared by dissolving 49.04 gram potassium dichromate in distilled water and dilute to 1 liter. So make up the volume to 1 liter. Therefore, it becomes 1 normal because this gram, 1 gram equivalent weight is there in 1 liter. Then another solution you need to prepare is ferrous ammonium sulfate. One solution. Ferrous sulfate, ferrous ammonium sulfate. Ferrous sulfate. So, dear students, you can see the solution of ferrous sulfate. This is ferrous sulfate, and you can also use ferrous ammonium sulfate. And sometimes it dissolves with little bit difficulty. So you can have little bit warm water, and you can also add some sulfuric acid into it, and it dissolves. So are you able to see the color? What is the color of this solution of ferrous sulfate? Pawan? Are you attentive? Are you seeing it or not? Or should I stop teaching?
Yes, sir. Yes, sir.
You are able to see it?
Yes, sir. Light green, sir.
Can you
Sir,
see?
light green, sir.
Very good. Light, very light green. Good. Potassium dichromate, huh? Yeah. So I'll show you. We prepared some solution for you, and also we will show you some, because you know you are not in the lab, so you can at least see something. So 0.5 normal means this is you can say n by 2 also. N by 2 also. 0.5 normal means half of the gram equivalent weight. So 0.5 normal, and you can also see this. This is, what is this? Anybody? If you have worked on this? Anybody knows about this solution? Hello? All right, this is potassium dichromate, 1 normal potassium dichromate. So, and this is natural color, it is without indicator. When you dissolve, it is red in color. And 0.5 normal ferrous ammonium sulfate can be prepared by dissolving 196.06 gram of 196.06 gram of ferrous ammonium sulfate in distilled water. Add 20 ml concentrated sulfuric acid, cool and dilute to 1 liter. That will be your 0.5 normal ferrous ammonium sulfate. Diphenylamine indicator, prepared by dissolving 0.5 gram diphenylamine in a mixture of 100 ml concentrated H2SO4 and 20 ml water. So diphenylamine is the indicator used in carbon estimated emission in this method. We can also use one other indicator in place of this, and you must remember name of this indicator. It is usually asked from you. Diphenylamine indicator is used, and if diphenylamine indicator is used, then you need to have concentrated sulfuric acid is required in all the cases, but this concentrated phosphoric acid, 85% CP, it is to be used only when diphenylamine indicator is used. And we need to use sodium fluoride also when we use diphenylamine indicator. That means if we are using this indicator, then concentrated sulfuric acid is also used. It is used in other case also. And then you need to have phosphoric acid 85% CP and also sodium fluoride. And you can see meaning of CP. 85% CP means chemically pure. 85% chemically pure. And on sometimes on certain reagents or certain salts or certain acids and bases or chemicals, you will find GR, AR, purified, OR. GR means, if GR is written, students think it is general reagent. It is not general reagent, it is guaranteed reagent. AR is analytical reagent. And sometimes you will find purified, sometimes extra purified. So these are actually business techniques, and overall there may be, of course, some differences in the purity. OR is organic reagents. Now, if you do not want to use a diphenylamine indicator, you do not want to use sodium fluoride, you do not want to use orthophosphoric acid, then you can simply take another indicator, which is phenanthroline. Phenanthroline is 0.25 normal, and it can be prepared from O-phenanthroline ferrous complex indicator. Dissolve 1.485 gram of O-phenanthroline monohydrate. Monohydrate means 1H2O, and 0.695 gram of ferrous sulfate in distilled water and dilute to 100 ml. So this is how in laboratory, you can prepare the 0.25 normal of non-toluene iron complex indicator. In market, it is sold as Ferrion, Ferrion. So ready-made Ferrion is also available from the market, or you can also prepare. Now, many times you need sieves in the laboratory, sieves of different mesh, different sizes. So can anybody tell me meaning of mesh? What is mesh in sieve? Mesh size. Sieves are before you. And sometimes it is say 50 mesh, 80 mesh, 100 mesh, 150 mesh, etc. So what is meant by that? Suppose it is 100 mesh sieve. Anybody? Is there any from soil science? Anybody knows about mesh? MESH. Dhyan. Pressing 2-4 minutes lagi, 5 minutes. No, nobody knows. Okay. Actually, mesh size means the number of holes in 1 linear inch. 1 linear inch. Now you will ask what is 1 linear inch. So length of 1 inch. In length of 1 inch, how many holes are there? That is your mesh size. So you can see mesh size is defined as the number of openings in 1 linear inch of a screen. A screen is for the sieve. For example, a 80 mesh screen will have 80 openings or hole in 1 linear inch. So you can measure 1 inch in length and count the number of openings. So linear measures are one-dimensional. Linear measures are one-dimensional, measuring length or distance along only one geometrical axis. So now we see the procedure. We have prepared the reagents, we know the reagents, and now we should know the procedure. And procedure is take 1 gram soil having passed through a 80 mesh sieve in a 500 ml flask. 500 ml flask. So this is the flask. This is the flask, 500 ml flask, where we put 1 gram of soil, which was passed through 80 mesh sieve. Thank you. Yes. So you can see one is blank. This is blank sample. I think you cannot judge the color of this from there. And this is your soil. This is having soil. So this is your Arnold-Mayer flask. It is known as Arnold-Mayer flask of 200. In this case, sorry, 500. This is 500, and this is also 500. So you have one is your sample where you have soil, and other is blank. So simultaneously carry out a blank. Now what you need to do in both you need to add 10 ml of 1 normal potassium dichromate. In this also and in blank also, you need to add 1 normal potassium dichromate solution. So this is basically an oxidizing agent, and it acts along with sulfuric acid. It cannot act alone. It needs sulfuric acid to produce chromic acid. And chromic acid is basically an oxidizing agent. So after adding 10 ml of 1 normal K2Cr2O7 potassium dichromate in sample as well as in blank, now you need to swirl. Swirl gently means, swirling means it is doing like this, shaking slowly or doing like this, swirling. Gently to mix the reagent with soil thoroughly. And immediately after it, say 2-3 minutes later, you can add 20 ml of concentrated sulfuric acid. Mix acid with soil by rotating the flask gently. You can mix it like this slowly. So now you have added potassium dichromate 10 ml and 20 ml sulfuric acid. This sulfuric acid is concentrated sulfuric acid of 1.84 specific gravity. Now, keep the flask for 30 minutes to allow the oxidation to proceed. Means 30 minutes waiting period is there, and then you can go for titration. This can be titrated, and for which we are doing the titration. Some of the potassium dichromate will be used in oxidizing the organic matter. However, out of 10 ml, some may not be used. So we need to see, we need to titrate that how much potassium dichromate has been reduced, which will be equivalent to organic matter. So this is the only only analysis where unused material or unused chemical or titrant or chemical is titrated. In most of the other cases, it is different. So here we will calculate or we will titrate the unused potassium dichromate. So now we will go for titration. Titration will be done with the help of ferrous sulfate, and I have shown you ferrous sulfate in the reagent. Now, how to go for titration? And before titration, now you need to add 10 ml orthophosphoric acid, H3PO4, and 0.2 gram sodium fluoride if diphenylamine indicator is used. So you can add these chemicals into the flask and then titrate the contents of flask with ferrous ammonium sulfate solution or ferrous sulfate solution. In our case, it is ferrous sulfate solution. So end point, titrate the contents until green color starts appearing. So this is actually dull green. You can see it is kind of dull green color. And when green color will start appearing, if more than 8 ml of dichromate are reduced, the determination should be repeated with lesser amount of soil. That means the soil was rich in organic matter. Therefore, you need to take the smaller sample. So there will be change in the color. Now I request Kerosene to show you the titration. He will show you the titration here. Kerosene. He is Mr. Pyare Singh, who is working in lab for last many years, and he is the person who is very good expert in this. So I think you are seeing the burette. This is burette. So Prakash, what is the spelling of burette? Spelling of burette.
BUYRET, sir.
No, galat. Any other person who knows the spelling of burette?
BURRETTE.
Galat. No double R.
BURET.
sir.
सब गलत बता रहे हो, all are wrong. Correct बताओ. Now see titration.
Sir, BURETTE.
Correct. And what is the spelling of pipette? Now you see he is titrating for you. And there,
PIPPET.
yeah, BURETT. Pipette.
PIPPET.
PIPETT. Good. Pipette. So are you able to see the titration? This is.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yeah, good. Now you see change in color. दूसरा रखना, दूसरा सैंपल वाला. नहीं वो इसी का ही प्यारा सा. ये रखो, दोनों साथ रखो, इससे फर्क कर देगा। Are you able to see the color? One is dull, you see dull green, and one is green. Are you able to see the color? I don't know.
Yes, sir.
Yes, sir.
So we must really thank you, Mr. Pyare Singh. He's really very wonderful person and very helping person. And if you come to IRA and in agronomy, PG lab, you can meet him. He helped all the students in their analysis work. So now you could see the end point. Titrate the content until green color starts appearing. You have seen the green color here. And normally color changes from blue to chocolate red. Chocolate red. This color comes when you use freon as indicator. And if you use freon, no need to use phosphoric acid and sodium fluoride. I will tell you why addition of these two is required when we use diphenylamine indicator. And you can see the bluish green to dull green color. You have seen dull green color. This is your dull green color. I don't know if it is clear to you, but this is dull green color. Now we discuss the reactions. Reactions, what happens? So as you know, the potassium dichromate was added 10 ml and 20 ml was, yes, it's not a 10 ml sulfuric acid. 20 ml. So 20 ml sulfuric acid was there and 10 ml potassium dichromate. So what happens? Why we have added sulfuric acid? Because it can produce chromic acid, and chromic acid is the oxidizing agent. So K2R2O7, this is potassium dichromate, sulfuric acid, and it makes chromic acid, CH2CrO4, plus potassium sulfate. So this chromic acid is oxidizing agent. So it will oxidize the carbon, but in doing so, it will reduce itself. It will be reduced. So you can see 3 carbon. Carbon is without, this is, you may consider it as elemental carbon or simple carbon without any charge. And then chromic acids, CH2CrO4, and in the presence of sulfuric acid, because sulfuric acid is already there in the flask. And then what this chromic acid will do, it will oxidize the carbon and CO2 will be released. And then chromous sulfate will be formed. This is chromous sulfate and water. And in this reaction, you can see the carbon is oxidized by chromic, the chromic, and this is oxidized to 4 valency. From 0, it has become +4, and chromous was +6. This chromium or chromous was chromium was +6, and it has reduced to +3. So you can see the reduction of chromium and oxidation of carbon. So the reaction in a concentrated acid medium is exothermic. So when you add sulfuric acid, reaction is very fast, and it is about 120 degrees centigrade temperature. The amount of reduced dichromate, the reduced dichromate is considered to be quantitatively linked to organic carbon of the soil sample. Means if your this potassium dichromate, more potassium dichromate is used, that means more carbon is there. Now you see reactions during titration. 2S2CrO4 chromic acid. Chromic acid is there, which is unused. Whatever has been used is already reduced, and this is unused chromic acid, and then ferrous sulfate, or you can take ferrous ammonium sulfate here. And then ferrous sulfate was the titrant. Ferrous sulfate was the titrant. In the burette, you have ferrous sulfate, and chromic acid is in the conical flask, and H2SO4 is already present in the conical flask. Then chromous sulfate is formed, and this is ferrous sulfate or ferric sulfate. This one is ferric sulfate or ferrous sulfate.
Ferric, sir.
Very good. This is ferric sulfate. Ferrous sulfate is FeSO4, and ferric sulfate is Fe2SO4 thrice plus 8H2O. So this is the reaction, and here you will get end point. This is the sample, and this is chocolate red color. May not be very visible to you. So chocolate red color comes when you use ferrion indicator. Ferrion indicator. So this is the reaction during titration. You have seen, if it is ferrous ammonium sulfate, in place of ferrous ammonium sulfate is the titrant, then you will get product as chromous sulfate, ferric sulfate, and ammonium sulfate and water, and also end point. So you can see the chocolate color. So chocolate color, it should be visible now. Chocolate color, I think you should be able to see. So this is when you use ferrion indicator. Is it visible, chocolate color? So
Yes,
calculation we will see in the next link. Thank you. I will stop share. So welcome back in the class. And now I think you are aware of these reactions. And in our days, when I was a student somewhere, so we used to make chromic acid by having this potassium dichromate and this sulfuric acid. So we will make the chromic acid, and that was used to clean the utensils or glasswares. Glasswares which are difficult to clean by ordinary cleaner, then one can make chromic acid, and it can immediately clean. Put little bit of this chromic acid into the glassware, it will clean it because it is very highly oxidizing agent. So, but care should be given. You should not use chromic acid carelessly. Otherwise you will burn your skin. Now coming to the calculation. See this part carefully. ml of 1 normal K2Cr2O7 reduced. This is the quantity of potassium dichromate, because we have taken 1 normal potassium dichromate. So what quantity is reduced? So, or that will be equivalent to carbon. So this is designated by the symbol S. You need to remember S. So how this S is worked out? Blank reading will be higher, because in blank sample there may not be carbon. If carbon is not there, that means it will not get reduced much. Very little will be reduced. So blank reading you will get high reading, and minus sample reading. Sample reading potassium dichromate is used to oxidize the organic matter. Thus you will have less reading into ml of K2Cr2O7 taken initially. Potassium dichromate in the beginning, we have added 10 ml. So we need to put 10 here and divided by blank reading. So by doing so, we will get ml of 1 normal K2Cr2 reduced, which is equivalent to carbon oxidized. Now, further calculation is like this. See the first line. Now you need to work out the organic carbon in soil in percentage. Suppose you want to work out in percentage, then how to do it? Is equal to S. Just now we have calculated the S. This is S, and this is S. This is how you calculate S. So you put this S here into 0.003. Now, how this 0.003 has come? This is gram equivalent weight of carbon. So actually in this reaction, I want to show you how this 0.003 has come. So in this reaction, this carbon is oxidized and it is having now 4 valency. Before it was having 0, it is oxidized and have charge 4. Chromium was having +6 and it is reduced to +3. So in the oxidation of carbon, the change in valency is from 0 to +4. Here it was 0, then in CO2, carbon is having valency +4. Then the equivalent weight of carbon in this oxidation reduction reaction is 12/4. So 12 is the, what is 12? What is 12? 1, 2. Vipasha, what is this 12?
Yes, sir.
What is this 12?
This is the atomic number of carbon.
Good. So 12/4. Is it atomic number or atomic weight?
Atomic weight, sir. Atomic number is 6.
So why you are keeping shy? No problem. We learn from each other. So 12/4, 12 is atomic weight. 12/4 is equal to 3. So 3 is the equivalent weight. So this is in this 3. Thus 1 ml of 1 normal K2Cr2O7, 1 ml of 1 normal. I told you when you multiply the normality to the volume, what you get milli-equivalent. When you multiply the normality with the volume, you get milli-equivalents. And then when you multiply milli-equivalent with equivalent weight, you get in milligram. So 1 ml of K2Cr2O7 was used, suppose, and 1 was the normality. So 1 into 1 will give you 1 into 1 will give you milli-equivalents. 1 into 1 will give you milli-equivalents. So here you get 3 milli-equivalents. You get 3 milli-equivalents. You can see thus 1 ml of 1 normal potassium dichromate will oxidize 3 milligram or 0.003 gram of carbon. This explains the factor 0.003 used in the calculations above. You can see it more. Milli-equivalent of K2Cr2O7 used normality into volume. Normality was 1. Volume was also 1. Volume was also 1 is equal to S. Milligram of K2Cr2O7, S into equivalent weight of carbon. So here equivalent weight is 3. So gram, if you want to convert into gram, then S into 0.003. So this is how you get the factor 0.003. So here you get organic carbon in soil in percentage, S into 0.003. So S was, what was S? This ml of 1 normal K2Cr2O7 reduced. So S into 0.003 into 1.3. What is this 1.3? Because factor of correction, this is factor of correction 1.3. The most active carbon forms oxidized. So it is not that all the carbon present in the soil will be oxidized. Only 60 to 80% carbon can be oxidized by chromic acid. So this factor was fixed at 1.3, considering 77% of the recovery. Only 77% recovery of the carbon, then factor is 1.3, 100 divided by 77. Because this method is underestimating. So you need to fill the gap by multiplying it by 1.3 into 100. 100 is 4%. Divided by weight of soil sample in gram. Organic matter in soil, organic carbon into 1.724. organic carbon in soil, organic carbon in percentage into 10. So these are the formula developed by our teacher, Dr. Rajendra Prasad. He already made them by some calculations. And this is based upon 77% recovery, this is 1.3. And 58%, 1.724 is the factor to convert it into organic matter. Carbon can be converted to organic matter. Now, organic carbon gram per hectare in 0 to 15 centimeter soil. Organic carbon in soil gram per kg, you have worked out. And then into 2.24 into 10 to the power 6. This is a weight of 1 hectare soil of 0 to 15 centimeter depth. And then organic carbon in surface 0 to 15 centimeter soil. Organic carbon in soil gram per kg into 2.24 into 10 to the power 3. So this is how you can do calculations. Now we will try to have some numericals, some problems related to it. And then you can ask anything in your mind. I'm there to make clarifications, to clear your doubts up to now. Any point? Anything you want to ask? All right. Now, function of reagents. Functions of reagent, you have used potassium dichromate. In the presence of sulfuric acid, it makes chromic acid, which is a strong oxidizing agent. Why we use ferrous sulfate or ferrous ammonium sulfate? To reduce the potassium dichromate, not reduce, which is unused in the carbon, unused. Diphenylamine, it is indicator. Phosphoric acid and sodium fluoride is used when we use diphenylamine indicator. It is just to complex iron in the ferrous sulfate. Potassium dichromate titration when diphenyl is used as an indicator. So it actually interferes with the oxidation process. So therefore, it is required to be complex with phosphoric acid and also with the help of sodium fluoride. So these are the functions of the reagents. Now coming to the interpretation of soil test results. So now you have worked out the carbon content in your soil. So interpretation can be done, whether it is falling under very low category, medium, high, or very high. So first row of the table, you can see where the analyzed carbon fall. So according to that, you can put it in the category and you can suggest the measures to increase the carbon content or organic matter content in the soil. So interpretation of results can be done. Now numerical number 1, a 1 gram soil sample when reacted with 10 ml K2Cr2O7. So actually 1 gram sample was taken and 10 ml of potassium dichromate was added along with 20 ml sulfuric acid. For 30 minutes it was kept and then it required 15.4 ml ferrous sulfate solution. It was required by the sample. But ferrous sulfate when titrated in blank required 22.2 ml to titrate 10 ml K2Cr2O7 and concentrated sulfuric acid. Calculate the organic carbon and organic matter content in soil. Organic carbon in soil is equal to your same formula as into 0.003 into 1.3 into 100 divided by sample weight in gram. 22.2 was the reading of ferrous sulfate when you have soil sample. When you have, blank sample. When you have blank sample. So this is the reading of ferrous sulfate in blank minus reading of ferrous sulfate in sample. You see in sample it is less into 10. 10 is the quantity of potassium dichromate used, 10. In the formula you have already seen it. This formula. ml of K2Cr2O7 taken initially. So it was 10 ml. So this 10 is quantity of potassium dichromate and all divided by 22.2. That is the reading of the blend. So the orange color figures or numbers will give you S. They will give you S. So S into 0.003 is the equivalent weight of carbon. This is equivalent weight of carbon in gram into 1.3, 77% recovery into 100, 104%, and divided by weight of the soil in gram. So because the weight of soil is in gram, therefore you need to multiply it by 0.003 gram. It is in gram. Thus, you get 1.19% of organic carbon in soil. And then soil organic matter you can work out by multiplying 1.724 and you get 2.059 as the organic matter percentage. Is it clear to you? Yeah, Shubham. Shubham, are you there?
Yes, sir. Yes, sir. Yes, sir.
Any doubt, anything you want to ask in this?
No, sir. No doubt.
Fine. Any other student? Now, this is for you to do. Those who are attending the class may try to do it. Here, instead of 1 gram, soil sample is 0.5 gram. When reacted with 10 ml K2Cr2O7 and H2SO4 for 30 minutes required 8.2 ml ferrous sulfate. So this is for sample, and ferrous sulfate when titrated in blend required 10.2 ml is for blend to titrate 10 ml of K2Cr2O7 and H2SO4, calculate carbon and organic matter. So please do it. I will flash you formula. Harinder, are you doing it?
Yes, sir. Yes, sir.
Okay, please do it. So such questions are asked in your entrance exam or some ARS examinations. So you need to prepare numericals also.
Sir, organic carbon 0.76% and organic matter content in soil that will be 1.32%.
Let me check. I don't know whether I did it wrongly or you did wrongly. You can match it here. And we can find out the mistake, who committed mistake. So You check
Sir,
your.
I took sample weight. I took sample weight as 1 gram instead
Sir,
of 0.5. That's why, sir.
organic content 1.
You can double it. You can check my answer whether it is correct or not. You can. I am also in doubt whether my answer is correct or not. What is your answer, Dian? I think
Calculating.
Shubham, what happened to your answer? How much it is now? You need to double it. Simply double it because you have taken 1 gram soil.
Yes, sir. Now it is same as yours, sir. After doubling it.
That means mine is also correct. So you see, it is 1.5% carbon and 2.64% organic matter. I just rounded it off. So you may be getting 1.28, 1.27, sorry, 1.5, 528 or 529.
Yes, sir.
So I think you can see it and practice it. And now we will practice some more numerical. Now this is the numerical. If your soil organic matter in the surface 15 centimeter has increased from 2% to 2.5%. Suppose in 5 years, 5 years before it was 2%, and now it has become 2.5%. How much additional carbon and nitrogen is stored in the soil? Means increased. Carbon has increased, and how much carbon has increased, and how much nitrogen has also increased simultaneously, because organic matter also carries nitrogen. In this calculation, assume that surface 15 centimeter contains 1.875 million kg. That means normally we take 2.24 into 10 to the power 6. 10 to the power 6 means 1 million. Or you can simply take 2.2 into 10 to the power 6 kg. Or you can say 2.2 million kg. Similarly here also, 1.87 million kg means 1.875 into 10 to the power 6 kg soil per hectare. And the CN ratio is 10. Once you have identified how much carbon has increased, organic carbon has increased, and you can quantify it. You can work out the quantity of the carbon. And then you can see from the quantity, you can work out the nitrogen. Because ratio is given. CN ratio is 10 and organic matter is 58% carbon. Organic matter contains 58% carbon. So from this you can work out the carbon. And then here carbon means organic carbon. And then you can calculate you can give the answer. Is this question clear to you? Can you do it or you can't do it? Anybody? Yeah, Shruti, can you do this question? Shruti? Hello? Are you there in the class? Hello? Shwetansh? Shwetansh? Are you there?
Yes, sir.
Can you do this question?
Yes, sir.
No. Okay. So I do it for you. Now you see, concentrate your attention here. First, you need to determine the carbon in the, determine the amount of carbon in the soil. Or how much is the increase? First, you calculate this. So increase in soil organic carbon, kilogram per kg soil. First of all, you need to calculate the increase in soil organic matter per kg soil. So it was basically, finally it was 2.5% and initially it was 2%. So 2.5% means per kg it was 0.025. In 1 kg carbon was 0.025, and when it was 2%, 2% means carbon per kg was 0.020 gram. I will show you how it is worked out. See the blue color. 100 gram soil with 2.5% soil organic matter will have 2.5 gram SOM. Correct? Because the concentration is 2.5%. So 1 gram will have 2.5 into 100 grams soil organic matter. And 1 kg or 1000 gram will have 0.025 gram SOM. So if your SOM content is 2.5%, your 1 kg soil will have 0.025 gram of organic carbon. Similarly, if it is 2%, it will have 0.020 gram organic carbon matter. So 2.5 or 2% of 1 kg. So ultimately, you see, additional gain or increase in carbon was organic matter. Sorry, organic matter was 0.005 per kg soil. 0.005 per kg soil increase. So increase of soil organic matter if 1 kg soil was 0.005. So increase of soil organic matter in how much was the weight? This was the weight of the soil. In Indian condition, we put 2.2 into 10 to the power 6. That can also be put here. Kg soil, it is 1 hectare weight of 1 hectare soil. So therefore, if you calculate it, 0.005 into 1.875 into 10 to the power 6. So now you know organic matter. Organic matter quantity is 9,375 kg per hectare. Any problem, any doubt to anyone? Okay. I think it is very simple thing you can understand. Now step 2 is convert SOM to organic carbon. Now we need to calculate the nitrogen. So therefore CN ratio is given to us. Carbon content in organic matter is also given to us. 58% was given. If you remember, in the question, it was 58%. Organic matter contained 58% carbon. So 1 kg soil organic matter contained 0.58 kg of carbon, 58% carbon. So 9375 kg soil organic matter contains 9375 into 0.58, 5438 kg carbon. Now we know the carbon and we also know the CN ratio. So CN ratio is equal to 5438. So you can calculate nitrogen. By ratio also you can calculate nitrogen. So how you can calculate nitrogen? Because every 10 kg carbon is associated with 1 kg nitrogen. C is to N is 10 is to 1. Therefore, 1 kg carbon is associated with 0.1 kg nitrogen. 1 by 10. Thus, 5438 kg carbon, 544 kg nitrogen. So you can calculate the nitrogen. This is total nitrogen in the soil. Any problem in this? If no problem, then you do this numerical. Or you can do it in homework. This is your homework. You can do it. A soil contains 1.2% organic matter and CN ratio is 10. Calculate kg per hectare of organic carbon and nitrogen present in 0 to 15 centimeter soil depth. Take the weight of surface soil, 2.24 into 10 to the power 6. Answers are given to you. You can solve this numerical and write in your practical record. Now, converting bulk density to mass, soil mass. So actually what is there? Most of the time when you do analysis is done and you get the result. They are in percentage, they are in milligram per kg, gram per kg, and they are required to be converted on area basis, on hectare basis or on meter square basis. So you need, with the help of bulk density, you can convert it into area basis. So results are expressed as the amount of element per unit weight of soil, like in ppm, percentage or milligram per kg. It is required to be converted on soil mass basis, concentration based on soil volume or area. The mass of soil in a specified area is given. Mass of the soil, area into depth into bulk density. So you can work out the mass of the soil. You know the area, suppose 1 hectare. Depth, suppose 15 centimeter. you write the depth in meters, and then bulk density in tons per meter square. So mass of the soil in ton per hectare, area 100 into 100 into soil depth into bulk density tons per meter cube. Soil mass per unit area at a specified depth is used to know the amount of the element or compound per unit area. So mx is ton per hectare or kg per hectare. Mx is the amount of element or compound per hectare. Suppose you are working out carbon, organic carbon. So amount of organic carbon in tons per hectare or kilogram per hectare is equal to Cx. Cx is your concentration of the element or compound in gram per 100 gram or milligram per kg. So you can write it here, concentration, gram per 100 gram, your carbon, how many gram per 100 gram soil weight was there. So put the value here into M soil. This is in tons per hectare. M soil means mass of soil to the specified depth. Mass of soil to the specified depth, ton per hectare. Now you see soil carbon. So in this case, suppose it is carbon and you want to work it out. So here M you can calculate in tons per hectare. This carbon you can calculate in tons per hectare. Cx is the gram per 100 gram. You can put the organic carbon and then multiplied by 2.26. 2.24 into 10 to the power 6, and whatever comes, you multiply that by this bulk density of the soil. So in calculating the mass of the soil, you can calculate from here area 100 into 100 into soil depth into bulk density. So you can calculate the mass of the soil actually this way. Carbon density. Now, density is another issue. Soil carbon in a terrestrial carbon sink and amount of carbon stored in soil is estimated in ton per hectare. This requires conversion of carbon expressed as percentage of the soil weight to weight per unit of volume. Carbon density tons per hectare is equal to carbon percentage into bulk density into layer depth into 10,000 into 0.0. Use this formula. This carbon percentage means carbon percentage is concentration of soil organic carbon in gram per 100 gram. Then bulk density in tons per hectare tons per cubic meter. Bulk density and 10,000 is the factor to convert value of ton per cubic meter to ton per hectare. This 10,000. And then multiplied by 0.01. 0.01 is converts gram per 100 gram to tons of soil organic carbon per hectare. So you can use this formula to calculate the carbon content in tons per hectare. Is it okay, this formula? This is less confusing. Estimating carbon densities, the general unit for soil carbon stocks are ton per hectare to its soil depth of 30 centimeter according to Kyoto standards. But normally here from farming angle, we take 15 centimeter. Increasing soil carbon concentration in soil usually result in decrease in bulk density. So these were the issues. If you have any doubt, I think many of you are not taking any interest in this course. If that is the case, then tell me. Are you taking interest in this teaching or course, or you are just sitting? Because I don't get any reaction from you.